Hello and a warm welcome back to my little YouTube channel. Trust you're all well and in good spirits. Ready to do some calculations today. pH, POH, Ka, pKa, Kb, pKb, Kw and pKw. It just rolls off the tongue. This is perhaps the topic that most students who are not particularly mathematically minded dislike the most. That is common throughout the world, I've noticed. So we start off pretty mundanely with a calculate the pH of a 0.5 mole per decimeter cube solution of H2S. That is H2S hydrogen sulfide. Apologies for my handwriting there. The assumption will be that the equilibrium concentration of the H2S is the same as the original concentration of the H2S, so there is no change in the original concentration. This is a weak acid. How do we know it's a weak acid? Well, it's going to give me the Ka value very shortly, I would hope. It will also give me the balanced equation, which is H2S with H2O in equilibrium. Notice it's not a full arrow left to right, it's not to completion, with hydrogen sulfide conjugate base and hydroxonium or hydronium ion H3O+. So we can write the Ka expression exactly the same as Kc. Ka is going to be our HS minus, our conjugate base, times our conjugate acid, over our undissociated hydrogen sulfide. We don't consider water. Why do we not consider water? Because it is large and constant, so we can remove that from the question. The Ka value for H2S, can get the pKa from your data booklet, unlog that and get the Ka, which in this case is 9.1 by 10 to the minus 8. Since the HS minus and the H3O plus ions are equal concentration, then we let them be x, and x times x is x squared divided by H2S. So solve for H2S, and we're going to get an answer for x equals 2.1 by 10 to the minus 4 moles per decimeter cubed. Once we have our x, which is going to be our H plus, we can just minus log to the base 10 of our H plus, 2.1 by 10 to the minus 4, giving the pH of 3.67. Our next problem we are going to have a look at. We are not going to be calculating pH, we're going to be calculating POH. So we know that pH plus POH is 14. The concentration of our carbonic acid today is 0.35 moles per decimeter cubed. We will make the same assumption here that we made in the previous problem, that the equilibrium concentration is the same as the original concentration. So 0.35 minus x, we're going to assume is still 0.35. For a less than 5% dissociation, this holds true. Ka value is given in the question, 4.3 by 10 to the minus 7. So we set up the equation. We have the conjugate base times the hydroxonium ion, the conjugate acid, divided by the original concentration of our carbonic acid. You can see where we are going. Perhaps you could pause the video now, have a go at the calculation yourself and see what answer you get, replay the video and see if you get the same answer as Mr. M for Chem. That will be a fantastic thing for you to do. It's worth outlining the equation. Again, water is removed, it's large and it is constant. So H3O3 minus H3O plus over H2CO3. Ka given in the question is 4.3 by 10 to the minus 7. HCO3 minus and H3O plus, same concentration, so we can just square that value, so x squared over 0.35 is 4.3 by 10 to the minus 7. Solve for x, 3.9 by 10 to the minus, and I can barely see that number there, 10 to the minus 4, I believe that is. pH that is 3.41, but that was not the question. The question was what's the POH, not what is the pH. So pH plus POH is 14. Take 3.1 from 14, and then you will find that the POH will equal there you go, well done. Third problem. So we're actually going increasing the level of difficulty as we go through this video for this next problem. So we don't want the pH or the POH on this one. We actually want the OH minus. Okay, let's have a think about that one. OH minus, what we're going to do here. We've got 0.5 mole per decimeter cubed cyanide. We've got the Ka value for hydrogen cyanide, HCN, as 4.9 by 10 to the minus 10, so it's definitely a weak acid. Same assumption as the previous two. Equilibrium concentration is same as original concentration. And we know the relationship that Kb is Kw over Ka, or Ka started as Kb times Ka. If you don't know that relationship, time to review my previous video and have a look at the roadmap for success in acid-base calculations. Substituting the value for Kw, 1 by 10 to the minus 14, that's in your data booklet. Ka is given in the question, 4.9 by 10 to the minus 10, giving an answer of 2 by 10 to the minus 5. The equation we're thinking about is a reaction of Cn- with water, and we've made hydrogen cyanide and hydroxide ion. In the same way that Ka is products over reactants, Kc is products over reactants, Kb is also products over reactants. Again, we ignore the water because it is large and it is constant. So we've got HCN times the OH minus divided by the Cn minus concentration. How do we get from here? Well, we've got the Kb on the left hand side that we worked out, 2 by 10 to the minus 5. Equivalent concentration, so it's x squared over 0.5, which is given in the question. So x this time is 3.2 by 10 to the minus 3 moles per decimeter cubed. Welcome to question 4. Again, let the question appear before you. Pause the video. I think you're getting better now. You should be getting better at answering these types of questions. And then have a go at answering the question. The best advice is always to just begin where you can. We've got 0.1 mole per decimeter cubed HOCN. It tells me it has a pH of 2.24. Calculate Ka. How do we get from Ka to pH? Well, let's have a look at the question to begin with. It's going to react with water. We're going to make our hydroxonium or hydronium ion, H3O+, with our conjugate base, which in this case is OCN-. I thought it would be useful if we used an ICE table this time to show you what little difference it does if we actually do use an ICE table. So let's have a look. Initial change equilibrium. Initial concentration HOCN is given in the question, which is 0.1. And of course at the beginning there are no products, so that's 0 each. So how do we find out the equilibrium concentration of hydroxonium and OCN-, the conjugate base? Well, helpfully it's given me the pH in the question, which is 2.24. So H plus will be 10 to the minus, or inverse log 10 to the minus 2.24, which gives me a concentration of 5.8 by 10 to the minus 3. So it's 0.0058 is the amount of dissociation. We could have made the assumption that equilibrium equals original on this one, and I don't think it would make a great deal of difference until the third or the fourth decimal place. But let's see what happens. So we've got 5.8 by 10 to the minus 3, which is what the concentration has increased of both of our products, equal amounts, because it's a 1-to-1 ratio in the equation. If that's what we've increased by in the products, that must be what we've reduced by in the reactant. So take away the 0.0058 from the 0.1, and that will give you 0.94. Oh, happy days. So now we've got our proton, 5.8 by 10 to the minus 3, so we can square that on the top of the Ka expression. Divide it by the concentration, which was given at the beginning. Slightly reduced now to 0.94 from 0.1. So that gives me Ka value of 3.5 by 10 to the minus 4. Okay, doing good. On to our next problem. I think we're on problem 5 now. So what's it going to ask us to? We've got pH of 1.5. This is the weak base ammonia. What's the pH of 1.5 mole per decimeter cubed ammonia? Given that the Ka value for the conjugate acid is 5.0, and that's a 0, times 10 to the minus 10. I think we're going to be using Kw, Ka, Kb relationships again, aren't we? Because how else we're going to get the data to answer the question? Well, Kb is Kw over Ka. Okay, Kw is 1 by 10 to the minus 14. Very good. Divided by Ka given in the question, 5.6 that is, times 10 to the minus 10, not 5.0, 5.6, that was my handwriting. That gives me 1.8 by 10 to the minus 5 for my Kb. So let's have a look at the equation for this reaction. We have ammonia. It's going to react with our water in equilibrium with our conjugate acid, NH4+, and OH-. It produces OH- in solution, which is why pH is high or alkaline for ammonia hydroxide solution. Products over reactants, NH4+, OH- divided by the NH3. We know all about the water now, large and constant, so it's removed. Kb were worked out on the left hand side, 1.8 by 10 to the minus 5. So what we're going to do about the ammonium and the hydroxide, well, X, same concentration as X squared, over 1.5 given in the question. We're not doing the ice table this time, we're just going straight ahead and making the assumption that the equilibrium is the same as the original. X is 5.2 by 10 to the minus 3. So this was wanted the pH. We wanted to calculate the pH. So POH minus log to the base 10 of 5.2 by 10 to the minus 3. And that gives us a POH of 2.29. pH POH equals 14. So pH will be 14, take away our 2.29. It was 11.71, won't it? My mental maths is working today. Yes, 11.71. And now our final problem, which will hopefully be the most challenging problem so far. So if you've got the idea of what we're doing, again, pause the video when the details are up in front of you, and then have a go at the problem. So I want to know H+. It's asking me H3O plus, no other reason than to show that it's hydroxodium and the proton is not stable on its own, it's protonated the water. In 0.6 mole per decimeter cubed, large M is shorthand for mole per decimeter cubed, sulfate, not just sulfate, okay, gives me Ka value 1.2 by 10 to the minus 2. So that's quite a small Ka value, isn't it? That tells me a lot about the strength of this sulfate ion. I'm going to make the assumption again, it's fair enough to do, that the equilibrium is the same as the original. Same pathway as before, Kb is Kw over Ka, 8.3 excuse me, by 10 to the minus 13. And this is for the reaction sulfate plus water. And we're going to make hydrogen sulfate. Now it's not 2 minus, it's 1 minus plus OH minus. Okay, so we made hydroxide ion. So Kb is going to be my usual product concentration over my reactants concentration. And you're ahead of me, right? We're getting rid of the water, we don't need the water. Very good. I worked out the Kb on the left, 8.3 by 10 to the minus 13, that's so small. X squared, equivalent concentrations, over 0.6, which is given in the question. So now X is going to be 3.1 by 10 to the minus 3. I need to work on my handwriting. So Kw, H plus times OH minus. So we know Kw is 1 by 10 to the minus 14. H plus is what we're trying to work out. And the OH minus we did is 7.1 by 10 to the minus 3. 7.1. So the answer is 1.4 by 10 to the minus 8.